Okay, here we go. So I'm just going to write on this piece of paper as I would normally write on the board. Yeah, hopefully that system improves as we move through the rest of the semester. All right. So today is lecture number 20. All right. So we're on chapter 12 still, pages 303 to 310, where we're going to cover in this particular lecture. For next class, read 314 to 328. Homework, well, I'll figure that out. Okay, so if you remember last class, before we had our exam and before all the other stuff happened, we had started rotations. So if you think you need a little refresher, maybe pause this and go look over your notes from when we started rotations. I'm just going to pick up right where we left off. All right. So today we're going to do Introduction to Torque, and we're going to do the parallel axis theorem. Okay. So if we have an object, oh, I should go get an object. If we have an object like this copy of J.R.R. Tolkien's The Hobbit, right? Oh, this is a bad example. I want something irregularly shaped. Do I have anything irregularly shaped? I don't think I do. Everything in my apartment seems pretty symmetrical. I'll just carry on with this. All right, so imagine this is irregularly shaped. And I know what the moment of inertia is if I put the axis of rotation through it, or through it this way, or through it this way. But maybe we want to know the axis of rotation displaced a little bit in some direction from where I know I have the correct calculation through the center of mass. So if I had my center of mass, my book is here, and I put my axis of rotation straight through, we can calculate or look up, you know, the moment of inertia if we were to rotate it this way, rotate it this way, or rotate it this way. But we might want to know what the moment of inertia is if I put the axis of rotation through here, so then the book would be sort of rotating like this. Okay, we could redo the whole calculation for a object with a continuous symmetry and a uniform center of mass, or excuse me, uniform density. But there's an easier trick we can use to figure that out if we have knowledge of the moment of inertia through the center of mass and how much it's displaced and how much that new this is really difficult without the board somehow. Without the new hold on. Pause. It's nice that I can just pause the lecture and collect my thoughts. Okay. So I'm just going to draw this. So imagine I have some weirdly shaped object, right? And we know where the center of mass is. Let's say it's here. Okay? And so let's suppose we also know what the moment of inertia is if we have an axis of rotation that passes through that center of mass. Now we might want to know, like I was showing with the book just a moment ago, what would be that moment of inertia of that object if I displace the center, or displace the axis of rotation by some amount to some new position, right? Now, if both of these axes of rotation are parallel, right, then we can calculate the moment of inertia about this new axis of rotation by starting with considerations of energy. So we know that the total kinetic energy of any object is given by 1/2 mvcm squared plus 1/2 ICM omega squared. Okay, so this bit here, right, that's going to be the kinetic energy added by this center of mass rotating about this new axis of rotation. So it's almost like the center of mass is going on a little orbit, and we can see that the contribution of the kinetic energy from that rotation, from that sort of orbital part of the motion, is given by our regular linear kinetic energy equation, 1/2 the total mass times the velocity of the center of mass squared. Now we add to that 1/2 ICM omega squared, and this takes into account that the object as a whole, is rotating about this. So we can split up the kinetic energy of this system into two parts. The part from this orbital bit and the part from, so orbital, and the bit from its simple rotation about this axis here, right? This is a little tricky to explain conceptually, but imagine I was sitting on this center of mass as this object rotated, right, about this other axis of rotation. Now there's going to be some contribution to kinetic energy because the center of mass itself is moving around, but if you imagine you're sitting at this point here, right, or standing as I drew it, then if I'm looking down at my feet and ignoring this orbital motion, I'm going to see the object turn beneath my feet, okay? And that's going to be this contribution over here, so we could call this the spin part, right? This is a general feature in physics that oftentimes rotational motion can be decomposed into two parts, the orbital and spin part. And here we're going to use this to trickily get the moment of inertia of this object, this irregular object, now through a different axis of rotation. So now if we want to have an object that has kinetic energy only from its rotation about its axis, not through the center of mass, then that kinetic energy is given by 1/2 IU omega squared. Okay, so why is this energy different than this one? Well, they're the same energy. They're both kT. They're both the total kinetic energy of the system. It's just that they're written in two different ways. This one is written in terms of the spin and orbital part, if we're looking at it like this. This one would be the kinetic energy, right, the rotational kinetic energy of just this object rotating about this bit here, okay? So that's the same amount of kinetic energy here and here, right? It's just written in two different ways. And this I sub u, this is the moment of inertia of some unknown object, or rather this known object, but we don't yet know the moment of inertia of it. Okay, since these two energies are equivalent, we can just equate them, and we end up with, after some simple algebra, IU omega squared equals MVCM squared plus ICM omega squared. Okay. So now for the axis of rotating, or excuse me, now for the two axes rotating parallel. Wait, no, I said that wrong. Hold on. Right. Oh, okay, I see. Sorry, my notes are a little poorly written. Now for the axis of rotation parallel, so this axis here, right? The center of mass is moving in a circular orbit around this axis of rotation. So this velocity, center of mass, is going to be equal to h omega, where this h, right, is the distance between the two axes. Right? In other words, this distance here. Right, let's draw it down here so you can see. Right? This is just this center of mass going around in this orbit, and we know that the velocity is just going to be the distance, the radial distance, times the angular velocity. Okay. So then we can just plug this into this guy up here, and we get I sub u omega squared equals total mass h squared omega squared plus I cm omega squared, and IU is equal to mh squared plus ICM. Okay? So this is the parallel axis theorem. It tells us the moment of inertia, right, of an object with some new axis of rotation given the old axis of rotation, moment of inertia, right? And we just have to add this mh squared. And of course we can invert this equation, right? In case for some reason we know this moment of inertia but not this one, we can invert this, and of course then we get ICM equals IU minus MH squared. Okay. So let's do an example. Right? So we're going to apply the parallel axis theorem like we often do. We're going to have a uniform thin rod. Okay. Y-axis, x-axis. Okay. So we're going to say that you have a thin uniform rod of mass m, length L, on the x-axis. Has one end at the origin. And now using the parallel axis theorem, we're going to find the moment of inertia if we move this axis of rotation over here to some y prime. Right? So we're talking about first, say my pen is the object. The difference between the object rotating like this from its end, right, and rotating about its center of mass like so, right, which would be this y prime, because this is a uniform symmetric object and we're just drawing our new axis of rotation directly through it. Okay. So we know from just before, right, that this I is equal to ICM plus MH squared. It's just from the thing we just derived. So now we're going to have IY equals IY prime plus M1/2 L squared, right? This distance here, of course, is L over 2. So that's that H from before. Right. So then I know my ICM, right? We're inverting this. We know this I here, right? Now we want this guy here. So that ICM is going to be equal to IY minus MH squared. And we look up this IY in a table, right? And that's just 1/3 ML squared, right? We'll assume that that's just given to us. I'll write that up here just to be clear. ML squared. So this is from endpoint. Okay. So then we have that 1/3 ML squared, and now minus M1/2 L squared, and we get 1/12 ML squared. Now, of course, we could have just redone this calculation and gotten that answer, right, using our integrative method for finding the moment of inertia of an object. But just with a couple lines of math, we can do it this way, and it's much easier. Okay. So that is the parallel axis theorem. Okay. So like when we started talking about kinematics, regular linear kinematics, we saw that at first we could describe what motion was happening, how acceleration influenced velocity, relative velocities, et cetera, et cetera, et cetera. We learned how all that worked. And then we started talking about why motion happens, right? So the reason that motion happens in linear systems is because of the thing we call force, right? Of course, you know that force equals mass times acceleration, right? So what if we want to know angular acceleration, right? Now we need a new quantity because this force isn't really going to work anymore. So we're going to introduce a new dynamical quantity that's going to play the part that force played in our study of rotational motion. Okay, so in order to start talking about this, let's consider the case of a merry-go-round. Okay, so in our merry-go-round, right, we're looking at our merry-go-round from the top, and the merry-go-round has a series of bars going around it, right, and the inside, or rather on the outside and on the inside, right, it's a large merry-go-round for some reason. Okay, so this merry-go-round is fixed by a pivot. Right here it can rotate that way, but it can't translate linearly in other direction. So I know that if I apply I know from just my experience from a kid on playgrounds that if you apply some force right here, right, directly into this pole and towards the pivot, of course it's not going to turn, right? I could apply some force here, and it'll turn a little bit, but I know that the maximum amount of turning I get is when I apply the force right at this tangential direction here. Okay, so if I apply my force here, that does something, although applying that same amount of force over here does nothing because it's just going directly towards the pivot. Also, and here's where I would ask you a question if we were actually in person and in class, and that question is, well, should I apply that force to this interior ring of pivots, or should I apply it to this exterior ring of pivots to get the thing to rotate as much as I want, right, or as much as possible? And of course, you know the answer is that I should use this exterior ring of poles, or whatever they are, to make the merry-go-round rotate. So why is this? If I want to cause a rigid object to rotate by applying a force, only the force applied tangentially matters, right? So this has no tangential component, right? It has no component pointing this way along the tangential direction. So I get no rotation. Over here, right, when I'm applying the force over here, all of this force is tangential. Okay, so then I get the maximum amount of rotation. So we can think of the merry-go-round as a system of particles, which could be these poles here, right? And any object can, of course, be thought of as a system of particles. And as this thing rotates around, right, it does so under the influence of some force. Okay. So to be clear, putting force in the centripetal direction does nothing. Okay. So now, oh, there's a staple in here. Pause. Okay, we're back. I'm really digging this. I can just pause the lecture and go do something. Okay. So if I want to cause the most amount of rotation for our merry-go-round or some other object, I of course want to push on those outer poles, and the reason is this. If I have a pivot here, right, and I'm moving my pole, let's say, from some initial position to some final position as it rotates around, right? There's R1. This is some angle theta, right? Let's compare this to doing that similar thing, but with a much longer distance, right, between the pivot and the object I'm trying to rotate. So this is the pivot, and this is still that same angle theta, right? If I want to rotate this other object by applying a force way further out through that same angle theta, it's pretty clear why I can get more rotation here than here if I think about energy, right? Because this path of this particle, right, if I have R1 much less than R2, I have a much longer path here over which I'm applying the same force, and we know that work equals force times distance in the simplest form, right? So even though I'm applying the same force here and here, over here I'm doing it over a longer distance, so I do more work, therefore I'm putting more energy into my system, therefore my angular velocity is going to be greater at the end than if I was doing it this way. So that shows you just quickly how using the idea of work and energy, it's pretty intuitive why it's better to apply the force as far away from the pivot as possible. Okay. So what we're going to do now is define a new quantity called torque. Okay. Torque is written with this funny looking t, which is the lowercase Greek letter tau. Okay. And work, our first definition, is going to be force applied tangentially, right, times the radius at which I apply that force, so this R1 or this R2. So for torque, I take only the tangential component. Okay, so that's going to be really important as we go forward. Okay, now, so continuing with our definitions, force tangential equals mass acceleration tangential. Okay, this is just our Newton's second law, but written just explicitly in terms of things that are tangential. I'm going to multiply each side by r, right, because I want to get at a relationship between torque and the angular acceleration. So this guy here, that's just my definition for torque that I just gave up here, right? And then I have mr squared alpha, and I got at that step in between here by knowing that alpha equals acceleration tangential divided by r, okay? Which is similar in form to this equation, which you're familiar with, right? Angular velocity is equal to tangential velocity divided by radius. Angular acceleration is equal to tangential acceleration divided by radius. So we're just taking this AT and subbing it into there, and then we get this equation here, right? Hopefully that's pretty clear. So now if we have many individual particles, or a rigid object, right, made of a collection of particles, as all things fundamentally are, I can find my torque net by just adding up all the individual components of all the individual particles. So the sum over j, mj, rj squared, alpha, right? I don't have to label the alphas because they all have the same angular acceleration, because we're talking about some rigid thing where everything's moving as one, essentially. And now this should be familiar, right? This is just our moment of inertia of that object, which gives us I alpha, and so I have torque net equals I alpha. So this is Newton's second law for rotational systems. Instead of having force equals mass times acceleration, I have torque equals moment of inertia times angular acceleration. So this is a really handy thing that with a lot of the angular versions of these kinematic and force equations, the equation is the same as your familiar linear one. I just put in, right, the new quantities. So I take my F equals ma, I take out force, I put in torque, I take out mass, I put in moment of inertia, I take out acceleration, I put in angular acceleration. Okay. So the next bit is figuring out what to do with this force tangential. All right, I'm going to get some more paper. I'll be right back. Okay, back. All right, so how do we deal with this tangential force? So let's go back to the example of the merry-go-round. Right? So here we have our pivot again. We're looking at it from the top. Okay. So imagine that we're just going to apply some arbitrary force at this point here, right? I could have drawn that force vector here to make it more intuitive, right? That I'm pushing on this point in this direction. But of course, you know, I can grab a vector and move it around anywhere I want. So I'm going to put it here just because that's a little more clear to decompose it, okay? So I first draw that r that's pointing to where I apply that force. And now this force vector is going to be decomposed into two parts. It's going to be decomposed into a part going in the radial direction,